In the previous lecture, we have defined the notion of a divisor that in some sense represents the finite set of places counting their multiplicities. In other words, with finitely many non-zero coefficients of the z combinations of the places. And for a given function, particularly, we consider the zero divisor and pole divisor to denote their all poles, or it's all, to denote its all zeros and poles, again counting their multiplicities. And we have observed that both are the positive divisors. And as a difference, or to represent all poles and zeros together of a given function, we introduce the notion of the principal divisor. And this is, of course, divisor because we know that a function x can have finite many zeros and poles, so that means the finite many coefficients will be non-zero in the sum. And for a given divisor, we defined its associated Riemann-Roch space. And particularly, we see that it contains functions. If we write the divisor A more explicitly by regarding its positive and negative terms, then indeed we see that this associated A space contains functions that must have zeros at each qj of order at least mj, and we also observe that these functions can have poles at pi's of order at most ni. So that means roughly these A spaces describes as the functions with given poles and zeros. And as a characterization, we also see that being x in the A space of A means that VP of x is always bigger than or equal to VP of the divisor A for each place P. And we have observed that indeed this is a vector space over the constant field K. And particularly for the divisor, zero divisor, we have observed that this is indeed nothing but the base field K. And when we have a negative divisor, we have seen that its associated A space is a trivial space. And for also equivalent divisors, so that means one is written as the sum of some principal divisor given by a non-zero function z. In this case, we see that their A spaces are charisomorphic, so that means if we are able to conclude that this is a finite dimensional vector space, that means they have the same dimension as a vector space. And to be able to prove that, as a first step, we have observed that if we consider two divisors, one is less than or equal to the other one, with respect to the partial order on the divisor set, by lemma 1.4.a, we have observed that the A space of A, smaller one, is a subspace of the bigger one. And the dimension of the quotient space in this case bounded above the difference of their degrees. So that means this is a finite dimensional vector space. Now, by using this lemma in proposition 1.4.9, we will prove that for indeed each divisor A, its associated A space is a finite dimensional vector space. More explicitly, if we write the divisor as, if you consider its partition with respect to positive and negative terms, so that means if we write it A plus minus A minus, here A plus and A minus denotes the positive divisors, then dimension of the A space is bounded above the degree of its positive term plus 1. And since a divisor has, this divisor can have finitely many non-zero coefficients, of course this degree plus 1 is finite. And in order to prove this statement, first let me note that the divisor A, when we write the divisor A plus minus A minus, this is always less than or equal to A plus, because this negative term is always less than or equal to 0 divisor. Then by lemma 1.4.8, we know that A space of the divisor A is subspace of the A space of the divisor A plus, and in this case it will be enough to see that the dimension of the A space of A plus is less than or equal to its degree plus 1. So for any positive divisor, if we are able to see this inequality, we will be able to complete the proof. So now our claim is that dimension of the A space of A plus is less than or equal to its degree plus 1. And since this A plus is a positive divisor by the assumption, again by lemma 1.4.8, we can see that A space of the 0 divisor is a subspace of A plus, and the dimension of their quotient is the difference of their, is bounded above the difference of their degrees. So in this case, it's bounded above degree of A plus. On the other hand, by the linear algebra, we know that the dimension of the quotient space is the difference of their dimensions. And from the previous lecture, we know that the A space of the 0 divisor is isomorphic to K, so that means it has dimension 1 over K. Let me write it as 1. So, and if we remove this 1 to the other side, we get the desired. So that means for every divisor, its associated A space is a finite dimensional vector space. And okay, the next natural question, we have a bound on the dimension, we have a finite dimension vector space. So is it possible to find, to compute its dimension, or is it possible to write its basis explicitly? And we will investigate the answer of this question when we talk about the Riemann-Roch theorem. But for the moment, since its dimension will be an important notion, from now on, we will denote it by the lowercase L of A. And we say dimension of the divisor A. So again, recall that in the previous lecture, we have observed that for equivalent divisors, their S spaces are isomorphic, so that means they have the same dimension. And it's also natural to ask that for equivalent divisors, can we conclude something about their degrees, and later we will see that they have the same degree. But in order to see that first, we need to prove the degree of the principal divisors are 0. But to conclude something about the degree of the principal divisors, first we need to do some observation on the zero divisors, degree of the zero divisors and the pole divisors. Here, let me briefly recall the statement of the proposition 1.3.3. It basically says that the degree of the zero divisor is bounded above the extension degree of the function field. And similarly, we have also proved that the degree of the pole divisor is bounded above the same extension degree, because these two rational functions are isomorphic as a field. And now in the next theorem, we will prove that indeed, instead of inequality, we will have equality with the extension, with the degree of the zero and pole divisors and the extension degree. And we will see that the degree of the zero and pole divisors are the same. And this gives us all principal divisors has degree 0. But before proving this theorem, let me try to give an example for this case. Again, if we consider the rational function field k of x, and if we write the non-zero function as a quotient of the relatively prime polynomials f and g, here a is a non-zero constant, and when we consider their factorization, since they are relatively prime, they are irreducible factors. These polynomials will be pairwise distinct polynomials. And in this case, the principal divisor offset will contain the zeros offset, counting their multiplicities. Here Pi denotes the places with prime element Pix, and Pix the irreducible polynomial. And we will also consider its pole divisors. So that means, in this case, counting their multiplices mj and the qj will be the place corresponding to the irreducible polynomial qj of x. And finally, we will also need to always consider the pole divisor. Here P infinity denotes the pole of x. And in this case, we can observe that the degree of the principal divisor is the sum of the degree of this divisor. It's always the degree of f of x. And similarly, degree of this component, this is degree of g of x plus degree of g of x minus degree of f of x, because P infinity is a rational place. So that means is of degree 1. And this confirms us the principal divisor z has degree 0.